Hey guys, in this video, I want to talk to you about introducing acids and bases. So far you guys have worked a few worksheets being able to name acids, being able to distinguish the difference between an acid and base, as well as how that relates to pH. So we're going to go a little bit deeper into those worksheets and understand kind of what AP is wanting us to know. So, first of all, there are different types of theories that explains an acid and a base. And so, if you pull out your NIMSY note sheet and just kind of take notes along with me or whatnot, then we'll be good to go. So, let's talk about the different theories of acid-base, okay? So the first theory of acid-base is known as the Arrhenius definition. And so that's what you see right here. The Arrhenius definition says that the acid donates a hydrogen ion, which is an H+, in water. So hydrogen ion is being donated by the acid. The base donates a hydroxide ion in water. So it's donating an OH minus. So this is called the Arrhenius definition. Now, there's a few problems with the Arrhenius definition, okay? The biggest problem is that it doesn't explain all bases, okay? Ammonia right here is the major exception. So ammonia is NH3. And if you don't know already, you need to ingrain this in your head, NH3 is classified as a weak base. Well, if we look at NH3 here, according to Arrhenius definition, a base is supposed to donate a hydroxide ion, an OH negative. Well, the problem is ammonia doesn't have an OH negative to donate. So therefore, we call this an exception to the Arrhenius definition. We do know that it is a weak base, but it doesn't fit this rule. So we have another theory that is a little bit better definition of an acid and a base. And that takes us into what we call the Bronsted-Lowry definition. Now, this is the definition that we work with in AP, okay? So anytime you're explaining, justifying an acid or a base, you need to always justify and explain according to Bronsted-Lowry. So let's talk about what this means. An acid donates a proton in water, okay? So it's giving up a proton. Now, if you work through those worksheets and you got what you're supposed to out of that, a proton is the same thing as an H+, a hydrogen ion. All right, the reason why hydrogen has one electron, one proton, and if it is a positive, that means it gets rid of its electron. So guess what a H+ is? It's just a proton. So that's why a proton is an H+. A base, on the other hand, this is where the definitions get different. A base accepts that proton in the water. So it's accepting this H+ from the acid. So this is a better definition because it does explain ammonia as a base. So this is what we're going to work with in AP. Now, I just want to show you that there is another definition. It's called a Lewis definition. You mainly use this in organic chemistry, okay? We do not do this in AP any longer. It used to be in the old design. Before the redesign, it used to have a few questions about that. Well, now they don't ask any questions about that any longer. Okay, so you do not have to worry about the Lewis definition of acid and base until you get into organic chemistry. So let's talk about this concept, Bronsted-Lowry definition of an acid and base, and let's apply it to conjugate acids and conjugate bases. When you guys were working with the worksheets, if you got what you're supposed to out of it, then you should already have an idea of what a conjugate acid and conjugate base is. What we have here in this situation, we have a couple of example problems. This is a typo. It should say H2O as my base there. So our first one, we have HNO3 plus H2O, and it yields H3O plus. If you remember, this is called the hydronium ion. All it is a water molecule that has a hydrogen attached to it. So I want to kind of just show that to you here. So we have a water molecule here. It looks like, upside down Mickey Mouse ears, or you can draw it where its Mickey Mouse ears, however you want to. So this is a water molecule. These are your hydrogens, and this is your oxygen here. Well, water is a polar molecule. And so what that means is that the oxygen end of this water molecule has a partial charge, and it's partially negative. Well, the hydrogen ends have a partial charge and is partially positive. What polar means is you have a separation of charges. So you have a positive portion on one end, you have a negative portion on the other end. Well, because this is a polar molecule, whenever this H plus comes into play, right? Remember, the H plus is being donated from the acid to the base. So you see how this water is accepting an H plus. Well, when that's the case, I have a little H plus moving around right here. Which end of this is it going to be attracted to? Well, it's going to be attracted to the negative portion of the water molecule. And so a hydronium ion looks like this. It's just a water molecule that has now a little H plus attached to it. And because it was neutral before and it got a positive charge, that's why this is H3O plus, the hydronium ion. And so, since we have the hydronium ion here, and it is a result of the base gaining that H plus, then that makes this the conjugate acid. The acid donated the proton to the base, and it now becomes NO3 minus, because you see how it's rid of an H plus here, right? So now it's NO3 minus. Well, that makes this now a conjugate base. What you learned from the worksheet is that your acid and your base, whether or not it's an acid or a conjugate acid, it's always the acid is always the one that is donating the proton. So if I were to go backwards, this H3O plus is the one donating the proton. So that makes this the acid. This is the one accepting that proton. So that makes this the conjugate base. So we have what we call acid-base conjugate pairs, a conjugate acid-base pair. And so my acid turns into my conjugate base. So my pair would be HNO3 and NO3 minus. And my base turns into my conjugate acid after it's accepted that proton. So this conjugate acid base pair would be H2O and H3O plus. So they do like to ask multiple choice questions dealing with this. Okay, they'll have you label, or not label, but identify the conjugate acid base pair on a multiple choice question. They could give you HNO3 and ask for what the conjugate base is for that, and different things like that. Now, there's something else that we also learned in that worksheet, and that is amphiprotic or amphoteric type of compounds. And so if we go to this next page, let me scroll to the next page for you guys. I believe that it's discussing those things. Let's see. It might be later on. Oh, here we go. So we're on page 3. Sorry, I'm skipping around a little bit. Amphiprotic or amphoteric. What that term means is that you can behave as both an acid or a base. So you can behave as an acid or a base. If you're the one, if it is actually donating the proton, then at that instant it's acting as the Bronsted-Lowry acid. If that species is accepting the proton, then that means that in that instant it is acting as the Bronsted-Lowry base. So there's a couple of examples that we can actually give. Water is an example of this because water can receive an H plus, so it can act as a base, receiving an H plus to make H3O plus, or it has a hydrogen it can give as well. It can give this hydrogen, give off the H plus to make OH minus. So any molecule that you see that could potentially receive an H plus and or give an H plus, that is known as amphiprotic or amphoteric. Let me give you another example of one. Let's see, we have H2 H3. I was going to give another example there. Pause one moment. Sorry, my brain wasn't wanting to work. Okay, so we have HSO4 minus, all right? This is also an amphiprotic or amphoteric species. The reason why is because, one, it has an H to give, so that means that it can be or act as a bronsted acid, or two, it can receive an H plus. The things that are mainly negative, have negative charges, that means that they can always receive H pluses. Some exceptions to that is water and ammonia in H3. Because NH3 can actually become NH4 plus. It can actually receive an H plus from there. Most other neutral things can't really do this, all right? But there are some exceptions to that. So if you have a negative charge something and it has an H on the front, however many H's, then that means it is amphiprotic. The exceptions to the negative charges are water, because we know that it can make H3O plus, and ammonia, because we know that it can make NH4 plus. All right, so that is known as amphiprotic or amphoteric. So I'm sorry I'm skipping around, but I want to take a second and go back up to page 2. What we have here on exercise 1 is it says that we have HBr plus NH3 yields NH4 plus Br minus. So this could be something similar to a multiple choice question. They'll have different answer choices or something there. So we want to figure out which one is the acid, which one is the base, and which one is the conjugate acid and conjugate base. So if I look here, this HBr has donated a proton to NH3. So that makes HBr my acid, which is hydrobromic acid. You should have known that from your naming acids worksheet. And NH3 is ammonia. What it's doing is accepting that proton. So that means that ammonia is acting as my base here. Now, the acid, once it donates the proton, it becomes the conjugate base. And once the base has accepted the proton, then it has become my conjugate acid. So therefore, my conjugate acid-base pairs would first be HBr, which acts as the acid, and Br minus, which acts as the base, and also NH3, which acts as the base, and NH4 plus, which acts as the acid. For part B, what is the conjugate base of H2S? Well, conjugate base is when I've gotten rid of an H plus, so that's going to make this HS minus. Do pay attention and understand and realize that you have to work with these charges here, okay? H2S is right now neutral because there's no outlying charge, right? So if I have a 0 charge and I get rid of a positive charge, right? Because it's not only an H I'm getting rid of, it's an H plus that I'm getting rid of. So if that's the case, I was 0, I'm subtracting a charge, so that's going to make this overall charge negative. What is the conjugate acid of NO3? That's a little minus sign there. So conjugate acid means that the base has accepted that proton. So I'm getting an H plus added to this. So if I'm negative and I'm getting a positive charge, that's going to make it neutral. So it's going to be HNO3 is the conjugate acid of NO3 minus. Now, when your acids donate your protons, it only donates one proton at a time. We have monoprotic acids, which means it donates only one proton. You see, it has only this one H that it can give. This H in the middle is squished. You can't really get rid of it. You can only get rid of this H in the front. Diprotic means it can donate 2 H pluses. So you see how there's 2 H pluses here. That means it's diprotic and can donate 2 protons. And we have polyprotic, which is an acid that can donate several, more than 2 basically, protons. And that would be H3PO4. Phosphoric acid is an example of this because it can actually get rid of 3 protons. The exception to that, though, is it only donates 1 proton at a time. And so what we actually see here is if the kind of step-by-step process, your first, if you have this stuff in water, H3PO4 plus water, H3PO4 is acting as your acid, and this is acting as my base. This is going to donate a proton. So we have H3O plus, and what we have left over is H2PO4 minus. Well, now I can get another H plus out. So I'm going to have another reaction here. I'm going to have H2PO4 minus. That's going to react with water as well. Water is acting as my base. That will make another H3O plus. Plus, now it's HPO4 2 minus. Well, guess what? I have another H to get. So I'm going to do a third step process. So HPO4 2 minus is going to react with water, so plus H2O. And when that's the case, it's going to get rid of its last proton to make hydronium ion, H3O plus H. Actually, that's wrong. There's no H's left, is there? So that product is going to be PO4 3 minus. And so what this is showing is the dissociation, the acid-base reaction for each proton that's being donated. I'm getting rid of 1 proton at a time. And another thing I want to point out is each process is harder and harder to get rid of the H plus, okay? So think of like this H just kind of attached to the phosphate ion, all these H's. Well, as I'm taking H's off, it's getting harder and harder for multiple H's to be getting rid of, all right? So the likelihood of this happening is far greater than the likelihood of this last H being given. Okay, you're mainly going to be stuck with all of this stuff. And we're going to kind of discuss that when we talk about Ka values. You also have polyprotic bases. And what a polyprotic base is when it accepts more than 1 H plus. All right, so these are the things that have your negative charges. They can accept multiple H's, so we call them polyprotic bases. All right, so I hope that's helpful for right now. All right, so that is all for my introduction to acids and bases. The things that you need to really know of, and this is a lot of multiple choice type stuff, is the different definitions, Arrhenius definition, mainly Bronsted-Lowry definition, what that means, how that relates to conjugate acid, conjugate base, and basically how to identify conjugate acids and conjugate bases from that. Okay, so I hope this is helpful. This is a good introduction, and we will continue doing more with acid base later on.